Okay, this is where we left off with last time. And as we look at the very bottom, okay, well, I shouldn't say as that's true, but when it comes to this, alkenes are highly reactive, okay? So alkanes are not. So upon doing that, what did we discuss yesterday that as far as these mechanisms are concerned or reactions? What's the difference between these two? Okay, that would be your alkenes. That's correct. So with that, do alkenes need a catalyst? No. But the exceptions then is that of hydrogen, which would need a metal catalyst. Okay. So when we're talking about this high stability or unreactiveness of these alkenes, we're saying that they need a catalyst, which would be true, ultraviolet light or heat. Then, when we're talking about these reactants, whether it's hydrogen, the halogens, or halogen halides, which would be hydrogen chloride or hydrogen bromide, and then ultimately water. What's the difference with the terminology between the halogens and halogen halide? Besides the name, I get that, but what would the difference? We drew it up on the board what the difference would be. Right. Everything you're saying is correct, but how do we determine what type of reactant it is? Is it the symmetrical type or the asymmetrical type? That's what we're asking what the difference is. So, of that term and that one, which one is the asymmetrical type? That should be hydrogen halides, not halogen halides. But hydrogen halides are asymmetrical. Then the halogens are symmetrical. Okay? So then water is also asymmetrical because you have a hydrogen ion and a hydroxide ion. That's what makes it asymmetrical. Okay. Yes. Yep. Wondering when you were having that discussion if your voice gets picked up from that far back or not. It might hear a slight muffle sound, but that's possible, yes. And I want to double check on this. Yeah. Hydrogenation, okay? Not halogenation. Catalytic hydrogenation. I thought that was the case because why would you be talking about halogens when we're just adding more hydrogens? So, catalytic hydrogenation. Okay. I suppose sometimes what happens, if you ever kind of out of your routine or something to that effect, when you're typing something and you get interrupted right in the middle of a thought or a sentence, well, then chances are you might pick up where you thought you left off. But yes, catalytic hydrogenation. Okay, so with this, notice we're still talking about alkenes, And if we're talking about catalytic hydrogenations, that means we need these catalysts. What would be the plural for catalyst? It would be the same, just like deer and deer and deer, right? One catalyst, two catalysts, or catalysts, I suppose. Okay. So as we look at these, okay, so you need to have a metal catalyst to add more hydrogens to it. That's the exception to the rule when it comes to these alkenes. Otherwise, those pi bonds are easily broken by any other reagent, and they attach in a specific manner, and that's what these next three slides will be dealing with. It's finally been getting cool enough at night to where now we can shut the doors and the windows and maybe only open them in the afternoon. Probably notice that as the day goes on, especially on the east side of the building. Oh, I have changed the meaning of I have a cough to just a few times. Okay. So as we continue then, okay. So why would oxygen be it's not an exception to it, but when we're looking at these types of reactions, if you have an alkene and you're reacting that with oxygen, what type of reaction might that be? It's a hydrocarbon and oxygen. That's a combustion reaction. That's right. Okay. So after this, I'm guessing we'll do one more slide to start illustrating these major and minor products, and that would be, yes, one more. That would be correct. So then finally, everyone have this information at once. Okay, so I want to do that one. Yeah. Okay. So this is going to be a reoccurring theme. Hydration, and then what's the opposite of hydration then? Correct. And we will see that concept this chapter, next one with the alcohols, and again with that of the acids, I believe. So, a lot of these terms that we're using now, especially this one in dehydration, we will be utilizing from now until probably into February. Okay, not so much this rule. Okay, this only pertains to what it is we're talking about right now. So you have to have the conditions just right for this rule to apply. Okay, pronounce it Markovnikov. Okay, you have to have the asymmetric reagent. So give me an example of an asymmetrical reagent. Hydrogen chloride would be one. Is added to an asymmetric alkene. So that's telling you where that double bond is. If it's asymmetrical, where is that double bond located? On the end. That's correct. And we'll illustrate why that is here in just a moment. Okay, does everyone have this information at once? Okay. Okay, so let's go through some of the progressions that we've learned so far this semester. For instance, okay, that's the simplest example that we could come up with. Okay, besides the organic family, what is that saying about each one of these compounds? Which one's saturated, which one's unsaturated? Say that again. Yes, that's correct. So then when we do this, it's just implying that bond after the first carbon. Okay, then we know here's your butane then. So with this, can we add more hydrogen to the bottom? No, because it's saturated. Can we add more hydrogens to the top? Yeah, sure we can. But what do we have to have in order for that to happen? That we do. That's the only exception to that, I wouldn't say rule, but what applies to that. But if we're reacting that with this, okay, I did that wrong. I meant to do this. Does that need a catalyst then? No. Well, what about this one? No, it's just the hydrogens. It was H and H, okay? So that first one, the two I's, what type of reagent is that? Symmetrical. This is then going to be what? Okay? Then same thing here. This is also asymmetrical. It's because how the ion breaks itself apart. Okay, then another thing that we had learned before this, which one has more isomers, the top or the bottom? Top one has 2, the bottom only has 1. Okay, so in other words, if we were to draw those isomers, the only one for this is that compound, 2-methylpropane, because again, if you move that methyl group either to the left or the right, you still have just a bent yeah, no. Yeah, no. Nope, 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 none of that. So then what we had learned, the isomers that we can do for this is just move that double bond over one and put a methyl group on there. Okay, now, however, what we want to do is let's go ahead and take this compound, we'll put it down here. Okay, so we'll switch it up just a little bit, even if it's like this many carbons. What type of, yes, I understand that's 2-hexene, or is that 2-heptene? 2, 4, yeah, 2-hexene, okay? So is that symmetrical or asymmetrical? It is symmetrical, okay? So in order for this to be asymmetrical, you would have to be over here or over here. And don't get hung up on how many carbons are on each side to make a mirror image, okay? The reason we say that, okay, is if we have this symmetrical compound and we're going to react that with, you want the symmetrical type or the asymmetrical type? Okay, so an example of an asymmetrical reagent would be what? H what? Okay, so as this proceeds, do we need a catalyst? No, no, because that bond is so weak and we're not adding hydrogen. Okay, so what we see happening then, we're going to have these 6 carbons. Okay. Get my weapon here. This fly is really starting to drive me nuts. The dramatic pause. I don't know if I got him or not. He's on my coffee cup. I don't want to swat him there. I think so. I don't see him flying around anymore. Okay. Okay, so now back to this. Okay, so where do you want me? These are both going to get used up. The hydrogen, 2 or 3. So we can put that hydrogen. The reason I got that different color so we know which one's which. So then now this would belong down here. Now we can't just put that. Okay, otherwise you're saying we're forming hexane. We got to account for that iodine went. So that's where that one goes. Yes. So the difference that we see here is the progression of this mechanism is if we change this to the asymmetrical type, okay, we can even just shorten it up 1 carbon because this is still going to be asymmetrical because that double bond is on the end. Now, one of the things that Markov-Nikov's rule said, you have to have the conditions just right to have a major and minor product. It said, 1, your parent compound has to be asymmetrical. This one is. This one was not. Okay? Then you have to have an asymmetrical reagent. So, give me an example of an asymmetrical reagent. Okay? So, this compound will react with one another. So now we got our 5 carbons over here. Okay? So now, the conditions are just right. An asymmetrical hydrocarbon and an asymmetrical reagent. Okay? So this breaks off here. So according to having asymmetrical and asymmetrical together, that hydrogen bonds to the carbon that has the most hydrogens. The author likes to say, well, the rich get richer. What that means is hydrogen-wise. So, notice we accounted for both of these atoms here. You could say, well, I thought that you attach that hydrogen with the one that already has the most. Well, there's only one of two places it could go, which was here and here. Well, this carbon had one, this carbon had one. So it's irrelevant which one you go to, because these are going to be formed in equal amounts. What you could do is say, well, what happens if the hydrogen ion attaches here and the iodine attaches up there? True. It's probably going to be somewhere around 45 and 49% or something to that effect. It would be equal amounts. Excuse me. This, however, when you have these conditions just right, both of these being asymmetrical, now you're going to have two products. So this hydrogen is looking for the carbon that it could attach to that already has more hydrogens. Okay? So it can't go here, can't go here, so it either has to go here or here. So, with that being said, this one only has one, this one has two. So therefore, that hydrogen is going to attach to the first carbon. Does that make sense? It attaches the one that has the most carbons available. So therefore, that hydrogen goes here. Then that leaves that chlorine atom to attach here. Then you have to label this as major. Okay? Then you would also have to put plus, okay, because you're going to have some of that left over, and I'll put that in a blue color. Okay, you're going to get the same thing. Same number of carbons, excuse me. And in this case, the chlorine attaches on the first carbon, the hydrogen on the second. Therefore, this is the minor product. Okay? So we got the major and then the minor. I don't know if this camera is not full screen or what. I guess it was. I don't know. Maybe it's not far enough back. Oh, maybe that's the problem. Because I thought it used to catch the whole overhead. Let's see if this works. Yeah, it helps, but not quite enough. Well, it's got most of it. Yeah, that's pretty good right there. Okay. So, is there any questions over that? So, especially this one. This one's probably the most difficult to comprehend. Are we good with asymmetrical hydrocarbon, asymmetrical reagent? Okay? Here we had an asymmetrical reagent, but the hydrocarbon was symmetrical. So that's irrelevant. You're just going to form one of two products. Then the last thing we'll do is if we have the hydrocarbon is asymmetrical and the reagent, however, is symmetrical. Just keep it simple with chlorine. Okay. Oops, I should have done that blue. Okay. So then these are going to proceed 1, 2, 3, 4, 5. Okay. So these two spots had a place to bond. Well, you can only go one of two places, the first and the second carbon. So we'll go ahead and put that chlorine atom there, and then this chlorine atom there. Okay. All right. Major and minor products. So get that drilled through your head. What's your hydrocarbon? Symmetrical or asymmetrical? What's your reagent? Symmetrical or asymmetrical? Those are the first things you're going to want to look at as far as what these mechanisms are concerned. We on the bus, left side? Right side, we on the bus? Alrighty, we will catch up to you next time.